Hey students, it's Mr. Lucido. In this video, I want to go over the 2 free response questions that were found in your personal progress check for Unit 2. Hope that you find this useful, and again, double check your personal progress check to go over your multiple choice answers. There should be explanations for each one as to why you got it correct or incorrect. And I should have your free response graded in the next couple days here. So let's take a look at question number 1. Okay, so question number 1 says, scientists are testing substance L to determine how it enters mammalian cells. Substance L to determine how it enters mammalian cells in a culture. The cells maintain a 120 millimolar intracellular concentration of substance L. So this is the concentration inside of these cells. The scientists determined the rate of entry of substance L into the cells at various external concentrations of substance L in culture medium. Okay, so they're placing these cells that have this specific concentration into different environments that have different concentrations of that substance. So this is all about how a substance is moving across the membrane, and we're measuring how fast it enters the cell. Okay, we've got our external concentrations on the left-hand side. This is our independent variable, and we have our dependent variable, which is how fast that substance is entering the cells. Okay, so we've got 4 questions here. The first question says to just identify the most likely mode of transport across the membrane for substance L. Explain how information provided helps us determine the most likely cause or most likely mode of transport. So we have to identify and explain. So if we look at the table, which I've copied in here just for our reference, again, we know that these cells, they maintain an internal concentration of 120 millimolar. And they're placed in these different environments. Now, if you notice, all of the environments are going to have a lower concentration than that of inside the cell. So we're always going from low to high when we're measuring, in this case, the rate of entry of substance L into the cell. So what type of transport moves substances from low to high? Well, that's active transport. So that's what we're going to identify first, active transport. And how we can use the information provided to determine that is what I just said. It's because in every trial of this experiment, the cells are placed in an environment that always has a lower concentration of substance L than inside of the cell. Right, and that's how we, again, use the information from this experiment and determine that it was active transport. Okay, question B is just asking you to construct a line graph with the correct scale and units to illustrate table 1's data. So again, we always put the independent variable on the x-axis, which was the external concentrations in this case, and then the dependent variable, which is the rate of entry, is going to go on the y-axis. And so here we have our line graph, which we'll use for question C. So question C says to determine the external concentration of substance L that will result in 1/2 the maximal entry rate. Well, the maximal entry rate is 100%. So where do we find a 50% entry rate? Well, so we just look right here, and we see that at approximately 30, maybe 32 millimolar concentration of substance L will give a 50% rate of entry. Okay, this last question says to predict the effect of the ability of substance L to enter the cells, which again is happening by active transport, if substance L is attached to a large protein instead of free in the culture. So we're looking at something like this, where we have substance L, we don't know exactly what it is, but it's attached to a larger protein. The most likely effect is that if this is initially being pumped inside the cell by something like a protein on the cell membrane, that if there's this large object attached, this substance is going to have a hard time making its way through that protein again. And so that would probably be the most likely effect, is that substance L would likely not be able to enter the cells if it is attached to a large protein. Okay, so that's our prediction. All right, so that's question 1, parts A through D. Let's go on to question 2. Okay, so for question 2, we're given a model that looks like a cell membrane with a membrane channel and a couple of substances like ions and lipid-soluble molecules on either side. So for questions A through D, let's go and walk through these. So question A said to describe the biological need for cells to be surrounded by a membrane that is selectively permeable for different materials. So first, selectively permeable, again, it means that it allows some substances to move across and other substances to not. And that can either be due to the properties of the molecule or if there is a channel for a particular substance or not. The biological need is, there's a couple of different things you could say here, but probably the most important is that this allows a cell to regulate which substances from the environment are able to enter the cell. And this is important to keep things that are toxic out and things that are needed allowed to come in easily. And ultimately, right, this protects a cell's internal environment, keeps it constant. Okay, now there's a couple other things you could say, but this is one of the main reasons why selective permeability is important. All right, question B. How does the model show selective permeability? Explain that. Of the membrane to specific ions. So for this question, it's asking about the ions that we see right here. All right, if you look closely, there are some ions that have polka dots and some that are just shaded gray. And if you notice that only the gray ions are actually able to move through this channel, not the ones with polka dots. And on top of that, they are not, both of the ions are not able to move through the bilayer like lipid-soluble molecules are able to, right? So that's selective permeability in this model, is that some ions can pass through the channel while others or other ions cannot. Both ions, however, in the diagram cannot pass freely through the membrane like other substances can, such as the lipid-soluble molecule. All right, and that shows it's permeable to some, but not permeable to other substances. All right, question C says, describe the characteristics of the phospholipid bilayer that permit small hydrophobic lipid molecules to pass directly across the membrane. So again, they're referring to this molecule right here. And the major characteristic of the phospholipid bilayer that matters here is that the interior of the bilayer, which is composed of the tails, the phospholipid tails, is hydrophobic. So hydrophobic substances are easily able to diffuse through this hydrophobic portion. That's the major characteristic that allows a substance like this lipid-soluble molecule to move through. All right, and then lastly, question D. Based on the model, explain whether the molecules shown crossing the membrane require energy to do so. So remember, passive transport is a type of transport that doesn't require energy, and active transport requires energy, and that's mainly because of the concentration gradient that exists across the membrane. So with active transport, it needs energy because it moves substances from low to high concentration. With passive transport, it can only move substances from high to low concentration areas. So when we look up here, it looks like the movement of molecules is going from top to bottom, and it looks like for all of these substances on the top, there's a higher concentration than there is on the bottom. And so we have both of these, or all of these molecules are being moved by passive transport because they are going from an area with high concentration to an area with low concentration. This does not require energy. Okay. And that is our response for question D. So I hope that was helpful. Please reach out if you have any questions. But again, those were the 2 free response questions from this unit's personal progress check. Have a good rest of your evening.